Welcome. This is now question 7 for AQA's AS Physics. This is June 2010, Unit 1. Okay, so in this question, I probably should have drawn a little diagram on the board actually before, but never mind. Okay, so we've got a diagram, a circuit even, where the battery, okay, it's got a EMF. It says electromotive force, but you should just know that it is EMF of 6 volts. Okay, and we've got a voltmeter which goes over the terminal of the battery, and you should know that if they refer to the potential difference of this voltmeter, which is the potential difference across the terminals of the battery, in other words, the terminals are these points here, then it is known as the terminal potential difference. Now, it's not the same terminal thing that you probably associate in A-levels, terminal life, but anyway. Okay, so we've also got a fixed resistor attached of 10 ohms. That's a bit clearer. 10 ohms. Okay, and yeah, so and it's got a switch as well. Sorry. So it's got a switch there. Okay, so we've got a switch, a voltmeter going across the terminals of the battery with a fixed resistor of 10 ohms. Okay, the first part, 7a part 1, simply asks us to define EMF of a battery. Okay, so you can do this in a number of ways. Okay, but I put the potential difference. The EMF is the potential difference across the terminals when the circuit is not complete. Okay, so it's the potential difference across the terminals you could say when the switch is open. And you go, why the hell have you come up with that? Well, the reason is, well, you should know that the EMF equation is equal to V plus I times little r. Well, little r is the internal resistance of the battery. Okay, and this V here, the potential difference, is a potential difference of all the components in the circuit. Okay, so in other words, it's just because there's only one component, the 10 ohm resistor, that V just relates to the potential difference of the 10 ohm resistor. And if we take that out, because we've opened the switch, in other words, we've not completed the circuit, we cross out that big V, the V that takes into account the potential difference of all components in the circuit. Okay, so therefore, E is equal to I times little r. And yes, that is little r, but that's still I times r, so it's still a potential difference. But that potential difference is the potential difference of the battery. Now, the reason we don't write I little r as V is because otherwise we'd have E is equal to V plus V, and that doesn't make sense. Okay? So that's why we write E is I little r, and this just says the potential difference across the terminals when the switch is open. Otherwise, or in other words, you could just say the EMF is equal to the current times the internal resistance, or you could say the electromotive force is the electrical energy. Oh, no. Yeah. Anyway, shut up. Okay, that was going on to A2 stuff there. You see, you do EMF in A2 as well, so if you are going to do physics at A2, you better like this EMF stuff. Anyway, okay, so that's 7a part 1. 7a part 2 says when the switch is open, the voltmeter reads 6 volts, as expected. Okay, when the switch is closed, it reads only 5.8 volts, so obviously it reduces by 0.2. Explain why this is. Well, you just said when the switch is open, when the switch is closed, a current flows through the battery, but it doesn't flow through. When the switch is closed, the circuit is complete, so the current flows through the battery and through the 10 ohm resistor. Okay. Hence, the potential difference is added of the terminals of the battery. Okay, because this voltmeter reads the potential difference of the battery. Okay, and if we are now closing the switch, we include the potential difference of this 10 ohm resistor. So the EMF is now distributed across the internal resistance and the 10 ohm resistor. So some of that potential difference is now attributed to this 10 ohm resistor. So the potential difference across the terminals falls. Hopefully that makes sense. Okay, because we're now including this 10 ohm resistor as well. Okay, there. Let's look at the next part of question 7. 7b says, calculate the internal resistance of the battery. Well, we need to go from this, so this is 7b, we need to go from the EMF equation, E is equal to V plus I little r. Now, it's asked us to work out the internal resistance of the battery, so obviously we don't know little r. But this V, remember, relates to the potential difference of all the components in the circuit. It's not relating to the potential difference of it's not equal to the EMF, okay? So the EMF we know is 6 volts, okay? So 6 volts is equal to, well, as I said, the V in that equation there relates to the total potential difference of all the components, okay? And we put that as 5.8 volts, okay? And that's plus I times little r. Now we don't know what I little r is, okay? But just from rearranging that equation, we get I little r, okay, so the current times the internal resistance to equal 0.2 volts. Okay? So, what does that tell us? Well, we still need to work out the current. Now, what is the current? Well, if we know that the potential, we need to look at this. Okay, this 10 ohm resistor. If the 10 ohm resistor, well, this V, when the switch is closed, we're now measuring the terminal, the potential difference of, in other words, this 10 ohm resistor. Okay, so what we will see is that this 5.8 volts relates to the 10 ohm resistor, because when the switch is closed, we're measuring the potential difference of this resistor. Okay, we said it's 5.8 volts, and we know, because we're told, that the resistance is equal to 10 ohms. So we can use V equals IR to rearrange to get I. So the current is equal to the potential difference, 5.8 volts, over the resistance, which is 10 ohms. Okay, so therefore the current is equal to 0.58 amps. Okay, so that's the current. And remember, the current is the same throughout the circuit. Okay, so it's the same in the battery as it is going through the resistor. Okay, so therefore we know the current is 0.58 volts. Okay, and so therefore we can sub in the current to be 0.85 volts. So 0.58 times the internal resistance is equal to 0.2 volts. So it's just a case of rearranging this to get the internal resistance is equal to 0.2 over 0.58. Okay, so therefore the internal resistance is equal to 0.34 ohms. And you can sub that into this equation and go back and just double check that means it works. Okay, and it should do, because you've just gone that way to calculate the internal resistance. Okay, 7c says, state and explain why it is important for car batteries to have a very low internal resistance. Well, if you think about it, if we times all of that equation by the current, okay, so we get the current, so the current times the EMF, which is essentially the power of the whole circuit, including the internal resistance of the battery. Okay, if we have a higher internal resistance, then more of the power is wasted, okay? Because when we times this all by the current, okay, so we get the current times the EMF is equal to IV plus I squared R, little r, or in other words, you could have IE is equal to I squared big R, okay, plus I squared little r. It's totally up to you. Okay, so basically, this I squared little r, that is, if we're defining the parts of this equation, we say that is the power wasted due to internal resistance. But the I times the EMF, that's the power supplied to the circuit. And then the IV, or I squared big R, that is the power which is used in the circuit to drive the motors, whatever it might be. Okay, so because the EMF of the battery stays the same, and the current obviously stays the same as well, if we have a higher internal resistance, oh sorry, the current doesn't stay the same. Is it? Yeah, it does. Yeah, if the current will stay. What? Yeah. The current will stay the same. It's just the potential difference that will we do. Anyway, So basically, if we the internal resistance, if that increases, well, this is a constant, okay? IE is a constant. So if the internal resistance increases, then more of the power that is supplied will be given to overcoming the internal resistance. And as car batteries need a very, very high current or power to start, if we increase the internal resistance, then if we increase any resistance, if anything, we'll decrease the current. So if we increase the internal resistance, then we're decreasing the current which is supplied to start the car. Okay, obviously, you have to be too much vision to start a car that is started by a very, very high current, and it's given straight to the starter motor. Okay, and it will crank the engine over and it will start the engine. Okay, so in other words, we need a very high current to start the car. Okay, and if we have higher internal resistance, then we have more energy wasted. Okay, more power wasted to heat or whatever, overcoming internal resistance, and less power supplied to actually start the car. So therefore, if we have a higher internal resistance, there's less chance of starting the car. That's essentially what 7C is saying. Now, I couldn't be bothered right now because I just go over my head. Anyway, so hopefully you understand all of that for 7C. I do apologise about the noise. There's a bit of a, but anyway, so thanks for watching, and we'll see you in the next video.